when we proved that the moment of inertia was this expression, what we did was we took a single object and we broke it up into pieces. And we said each piece is experiencing a force in order to accelerate. And then we added up all the pieces and we derived this by adding up all the pieces. Do you remember that from yesterday? So what I'd like you to do is I want you to calculate something. And we're going to use the meter stick as our example because it's easy. I want to break the meter stick up into 10 individual pieces and calculate what its moment of inertia is. So I have a meter stick, or at least what I'm going to use is a meter stick, and I want to divide it into 10 pieces. So my meter stick, let's see, in the middle, 1, 2, 3, 4, 1, 2, 3, 4, 10 individual pieces. Now, if I want to calculate the moment of inertia of the meter stick by breaking it up into pieces and using my summation formula, I think you could all agree that as a meter stick goes, the center of each piece would be the center of mass of each piece. Right? Our moment of inertia formula adds together point masses. And although this isn't a point mass, each of these centers represents the center of mass of a piece. You follow what I'm saying so far? So we're going to add together each piece. Now to do so, I want to do the moment of inertia about the end here. So if you don't remember, moment of inertia is a summation. And we're going to do this from I equals 1 to 10 because there are 10 pieces. Now, we know the meter stick, but I'm going to do this as a generic rod, even though I'm using the word meter stick. So we're going to say the rod has a mass of m and a length of L. All good? All right. What is the mass of one piece of the meter stick? 1/10 m. So our first piece, the mass part is 1/10 m. And how far away is the center of that piece from the end? It's not a tenth, because a tenth would be here. It's not 0, because 0 would be here. 1/20th, because it's in the middle, right? So it'll be L over 20. But remember, the distance away from the axis of rotation is squared. All good? Let's go to the next piece. What's the mass of the next piece? Each piece is the same size, right? So what's the mass of the next piece? 1/10. And how far away from the axis of rotation is its center? 3/20. That's right. Do you guys see why it's 3/20? Look at where the dot is. This is 1/20, so that's 2/20, and then 3/20. So 3L over 20 squared. Now, is that enough for you to figure out all the rest real fast? Do you see a pattern developing? We'll go one more. Let's go one more. The next piece is 1/10 m, and how far away is its center from the axis of rotation? There we go, 5/20. And so on and so forth until we make it to the last piece, right? Where the last piece will be 19/20 away from the axis of rotation. So last piece, 1/10 m and 19L over 20 squared. All right. Let's get the fraction, right? We can do this. Do you notice there's a lot of common elements to our summation? You guys have studied, because you guys are in calculus. Who's in calculus? So all of you finished pre-calc already. You guys did recursive formulas in pre-calc? Did you guys do that? So you can probably come up with a recursive formula to do this. There's a reason why recursive formulas exist for stuff like this. But we're not going to do a recursive formula. Let's factor out what we can factor out. I think we can factor out a 1/10. Do you guys see that? And we can factor out a 1/20 squared. Do you guys see that as well? Every term has one. So I'll factor out the 1/10. I'll factor out the 1/20 squared. I can factor out an m from every term too, right? I can factor out an L from every term squared. Do you guys see how every term is going to have that in it? And then we are left with what? 1 squared plus 3 squared plus 5 squared plus 7 squared plus 9 plus. Excellent. So you guys get the idea? I assume you have all of the squares up to 15 memorized, don't you? Don't you?
Yes.
Excellent. I don't have after 15. I stopped at 16, but you should have up to 15, I think. So 1, 9, 25, 49, 81, 121, 169, 225, 289, I think. Be able to check my work. I don't know 19. 361 maybe? 361. There. That all of them?
You're right.
All right. Add them all up. Add them all up. I know what the answer is, but you should do it. Add them all up. Come on, I have a bunch of mathletes in here. Come on, math nerds. The squares have power. There we go. Come on, only like 3 minutes left. 1330, thank you. So, if we take this and put it together, we will have 1330 over 4,000, right? Because that's 10 times 20 squared is 4,000. ml squared. Is this the moment of inertia of a rod about its end? This works out to be 0.3325 ml squared. But if you look on the board behind me, where we actually have the moment of inertia of a rod about its end, you'll notice that the actual expression is 1/3 ml squared. So the actual moment of inertia of a rod is 1/3 ml squared. We got a value that's a little bit less than that. It's not an accident. We played a little fast and loose with the rules because we said that each individual piece was a point mass. But if you look at our meter stick, this portion of the piece is closer to the axis of rotation than this portion of the piece. Because of that, we weren't perfectly accurate. We just averaged it out at the middle. And we did that for every piece. If we want to get a more accurate portrayal of the moment of inertia, we should break this up into more pieces. Perhaps 20 pieces, or 100 pieces, or 1,000 pieces. And you guys in calculus understand that the role of calculus is to take this and break it up into an infinite number of pieces. So how many of you are in A, B, or B, C? So all of you have reached the point now where you've taken those graphs and you just broke them up into lots of little rectangles. And then maybe you even went further and started breaking them up into little trapezoids, right? Have you made to that one yet? And you understand how tedious that is. What you're supposed to be learning is an appreciation for this summation. That's what we just did. We did the same summation you did when you found the area under a curve by breaking it up into rectangles. We did it, though, using moment of inertia, because for us, this is a physical property we're trying to measure. Next week, we got to do the calculus. And for some of you, that's going to be a challenge. I want you to be able to regurgitate the proofs. Everybody understand? We're going to do the proof for a line about its, or I'm sorry, a rod about its end, a hoop about its middle, and then the hardest one, a disc about its middle. We'll do all three of those. And you'll understand for a moment that it's not about the calculus. The thing that I'm going to teach you next week is how you set up the integral. The integral itself is easy. That's a process, and it's an antiderivative, and it'll be a polynomial. It's setting up the integral that's the hardest part. And we talked about torque and Newton's second law in reference to torque, which says that torque is equal to I times alpha. And the net torque and alpha are both vector quantities, and I is our moment of inertia. The way we use moment of inertia is a little different than what we had to do with inertia for other products. So consider something very simple for a moment. Imagine that thing I have over there, that our spinny thing, but instead of it looking like that, let's say I have a a disc and I mount it about its center, and I just hang a box off the edge. So something like that. The box is going to experience a force due to gravity. The disc is going to experience a force due to gravity, but the disc is mounted. So the disc is experiencing, in this case, 3 forces. It's got weight downwards. It's got some kind of normal force upwards, but it's experiencing a tension at the edge. Does that make sense so far? The box itself, we already know how to handle the box. The box is experiencing 2 forces, and those 2 forces are weight and tension. Now, we've seen problems like this before. And one thing I want to remind you about is the tension in that string is probably less than the weight of the box. Right? The system's probably going to accelerate, and the box is going to kind of start accelerating downwards when we release it. Does that make sense to all of you? So our net force of the box will probably be something like mg minus t equals ma. The net force on the disk is going to be 0. But the disk is going to spin. The net torque on the disk is not 0. This is an Atwood machine too. All right.